Hello, everyone. We are happy to be here with my colleague Max to give a talk on our work on Android data encryption. So my name is Damiano and we both work at Quarks Lab. We are mostly focused on embedded security research, especially on low-level Android related projects. And this research was actually triggered by a conversation that usually arises after conferences. Last year we did a couple of presentations where we delved into the Google Titan M chip, a security chip that has been added in Google Pixel devices to provide some additional security features. And someone reached out to us by email asking us whether we could provide any help. Their device, I think, fell into water, yes. And they had done some hardware work. They discovered the main SoC was dead, but the Titan M chip that actually lives a bit separate from the main SoC was actually alive. So they wanted to know whether we could help, given our expertise on that specific chip, to recover the data that they had lost that were inside the phone. So it's always a bit funny when you get these questions. You never know if it's someone that really has a problem or if it's like a shady agency that needs help. Anyway, the answer is no. Like, there's not much you can do because the main SoC and the Titan M work together when it comes to data encryption. But we didn't know exactly which was the role of the chip in this specific situation. So basically, this was the trigger for us to say, okay, let's dive into this and try to discover in the detail how the whole system works and how a security chip makes it more secure than when there is no such thing. So we took the approach of a kind of forensic analyst that may have access to a whole range of software vulnerabilities. What do you have to do to get the data out of a phone? And well, of course, there's credentials in the way. So, how does authentication play a role? And how would the two approaches change when there is and there is not a security chip? So again, we will present a couple of proof of concepts to reply to this question, focusing only on software bugs. So, no hardware attacks or cryptographic things for this talk. But before that, we're gonna give a bit of context so that we make sure we are all on the same page. First of all, we're talking about data encryption at rest. So we are basically in front of a situation where an attacker can do anything with a powered off device, with full physical access. And the feature itself is the one that allows data to be always stored encrypted in storage and be decrypted on the fly when loaded in memory, encrypted when written back. In Android, this is made possible by two features. One is Android full disk encryption that was later replaced by Android file-based encryption. The first one relies on dmcrypt, while the second one on FS script. The difference between the two is not really interesting. Again, FB is the standard since Android 10. So yeah, the support for this feature goes down to the kernel, basically at file system level. And essentially every file is encrypted with a different key. With a master key that is derived for the directory tree. Metadata are covered by an extension of FS script. So yeah, they're encrypted separately. The fact that each file has its own key turns out to be very useful for the whole Android OS, and there's a couple of features that have been introduced thanks to this property, such as direct boot and multi-user support. At the end of the day, we can think of how data is encrypted in Android in two ways. There's credential encrypted data and device encrypted data. CE data are only available after the user has authenticated, while with device encrypted, they can be available immediately after boot. So two encryption levels, two keys, the DE key and the CE key. We will mostly talk about how the second one is derived, because the DE key is derived automatically when you boot the device. There's anything that the user needs to do, so it's just automatic. So, to give you a concrete example, this is a folder where /data/data is a folder where applications are usually storing the user private data. And before, when you first boot the device, but you haven't authenticated yet, this is what you will see. So, a bunch of encrypted file names. This is just garbage. And as we said, we will talk about how the credential encrypted key is derived. It requires the user to authenticate, and it will start from these files that you can see on the screen. These are DE encrypted files, so they're automatically decrypted when you boot the device, and they're the starting point to get the CE key. To immediately answer to one of the questions we started from, user credentials are used in the process directly. So they need to be considered as raw inside the key derivation process. This means that it doesn't matter how many bugs an attacker can have. At some point, they are also going to need the raw string of your credentials. So going on with the background, since we will be talking about trusted applications, just a couple of words on trusted execution environments in general. Modern OSs have this distinction between a secure world and a non-secure world. In the non-secure world, we run, in this case, Android. It's an environment where the user has a lot of power, in some sense, to install applications, do stuff, while there is a parallel environment that is supposed to be isolated and safe, where the operating system is trusted, the apps need to be signed and verified before being run, and let's say this environment is supposed to be more secure than the normal one, and has access to some protected hardware resources. Last bit of background is the one on the Android key store system. So that is the system that Android has in place to create and manage keys. Keys are normally stored in the file system in the form of key blobs. These key blobs contain the key material itself, usually encrypted, and some further metadata. The idea is that there are different protection levels, and the raw key material can only live inside the protection level it belongs to. So if a key is TEE protected, it can only be used from inside the trusted execution environment. When it is outside, so in the file system, for example, it will be encrypted, so you can't see the actual bytes of the key. So for example, imagine at some point the normal world needs to use a key. It will send it to, again, the environment that is appropriate for that key. Can be the key master trusted application, or can also be a security chip in case of Strongbox protected keys. In this environment, the key will be taken out of this key blob and will be used to perform the operation, for example, a signature or an encryption, and we will receive back the output of the operation without ever seeing the key. All right, so having said this, we're going to start talking a bit about how the key is derived. And when we mentioned there are many complex steps, this is more or less what we mean. The schema is pretty complex, and it's also probably unreadable in this slide. So we're going to scope down to some specific parts and see what happens. And the first one on the top is the part where authentication takes place and where credentials enter the schema. So credentials, as you can see from the schema, go through script, which is a key derivation function that makes it costly to perform hardware attacks. Just a note, when we talk about credentials here, we talk about PIN, password, or pattern. If you think about it, the first time you boot your Android device, you have to put the actual credentials. You can't use biometrics. So the credentials are stretched, and then they form this token that is combined with the file, one of those you saw earlier, to create an application ID. But we only move forward from here if authentication is successful. So there is this token needs somehow to be validated. And here is where the Gatekeeper trusted application comes into the equation. The Gatekeeper TA is, of course, a trusted application, so it runs on a trusted execution environment and will take care of verifying this token against what we call password handle. So the original, the token that is that has been computed with the correct credentials. If the two match, Gatekeeper produces an authentication token. So yet another token. We'll be taking care of many tokens today. This token is the one that will prove to the system that authentication has occurred and has been successful. And it will allow other components to actually prove that the user has authenticated. So of course, Gatekeeper implements throttling, so you can't perform brute force directly against the trusted application. So in practice, what happens is that the user tries to authenticate. The system creates a password handle and creates a current handle and sends it together with the original handle to the Gatekeeper TA with the verify command. The TA will perform the NHMAC on the current authentication attempt, the current handle, and if the two match, it will mint an auth token and return it to the normal world. While if the authentication fails, it will just update its throttling counters and send back an error. So going back to the original schema, now we know that at some point we have an application ID, the one you see over there, and the next steps are the ones that take us to retrieve the synthetic password. So the synthetic password is kind of an intermediate password that is not yet the CE key, but from here on the process is automatic. So once you have the synthetic password, the user doesn't need to do anything else. Credentials aren't used anymore. And one of the reasons the synthetic password exists is also to kind of create an intermediate thing between the credentials themselves and the key. Imagine the user wants to change credentials at some point. You don't want to change the key itself. So it's good to have something in between. So the way the synthetic password is retrieved is through two AES decryption. The first one happens using a key that is TEE protected. So if you remember what we talked about earlier, there's a key that lives in the trusted execution environment. This key is authentication bound. So to be used, the key master trusted application will have to use the authentication token that has been created by the Gatekeeper trusted application to use this key and do the first AES decryption. And the second one will come thanks to the application ID that we generated after the credentials. So there is these two decryptions, and then we get the synthetic password, and from there on, everything is sort of downhill. So if we stop for a moment in this part of the schema, we can start thinking about how an attacker could try to mess and could try to attack the schema. And the first thing that becomes clear is that you need to tamper with the trusted execution environment. And there are two alternatives. Either you focus on the key master trusted application, so you are able to access the first AES key that, as I said, can only be used after authentication. Or you target the Gatekeeper trusted application so that you can actually forge authentication tokens regardless of the credentials that you have inserted, and from there on you can actually go on with the second with both AES decryptions normally, even if the user hasn't successfully authenticated. So I'm gonna give the floor to Max so that he will explain a bit how from here we go with our strategy.
Thank you, Damiano. So as Damiano said, there are two ways to create a proof of concepts in order to retrieve the credentials. And we actually decided to go with the way that involves the Gatekeeper trusted application. And so before I get to the actual POC, let's summarize a bit the strategy, our strategy to get into it. So The first thing is that we need to have enough privileges on the device, because there are these device encrypted files that we need to access in order to set up a brute force attack. And the other thing that we need is to actually patch the Gatekeeper trusted application so that it will accept any credentials and generate automatically the authentication token. So in order to reach that state, we need either multiple bugs, code execution on the device, then privilege escalation up to the TrustZone application, or simply one critical bug that happens early enough in the boot process so that we can bypass the whole secure boot and patch all the components we need, which is actually the strategy we followed. We decided to work with these two Samsung devices. And the funny thing about these devices is how we found them. We were looking for devices with a boot ROM bug, or at least a bug that impacts the boot system, the boot process. And we were looking on brick tutorials online, and we discovered some where people were not supposed to do what they were doing without a serious vulnerability. And actually, they were using a tool that I will present later on. So these two devices, they are behind, on the SoC level, they have two Mediatek chips that have a boot ROM vulnerability that we will exploit here. On the firmware side, they are a mix of code from Mediatek and Samsung. And for example, the TrustZone OS here is called Tigris, which is the TE OS designed by Samsung. So let's get into this boot ROM vulnerability, and we're not going to give too many details about it. Actually, we didn't discover that bug. It was already exploited on the wild, and there is this project called MTK Client, developed by John Kerler and along with other people. And this tool actually exploits a bunch of boot ROM vulnerabilities that impacts plenty of Mediatek system on chip. And actually the one that is involved here, the bug that is actually exploited on all devices, is probably placed into the USB driver of the boot ROM. But we won't give more details about this bug. We are actually using that tool to rewrite all the partitions we need to patch. And the tool also allows us to boot a modified preloader image. Preloader is the second bootloader in the boot system of Mediatek. And it will automatically disable the next stages, the next verification for the secure boot. So we can simply use that tool to bypass the secure boot and load a modified preloader, disabling the next steps. So if you ever encounter a Mediatek chip, I really recommend you to use that, to take a look at this tool. It's probably already exploiting some bugs in the boot chain of your chip, and it works quite well. So yeah, you will find the link here. Now let's take a look at the boot process. So we have the boot ROM, and this is where we have the bug that is exploited by MTK Client. Thanks to the tool, we are booting a modified preloader, and it means that the next steps you see on this graph, or the next verifications are disabled. So we can actually patch, for example, the Tigris OS. And we need to patch Tigris because in the end, what we want to achieve is to patch the Gatekeeper trusted applications, and there are some verifications happening inside the TEE environment. So we need to patch that. We also want to root Android, and the next bootloader that is here called LK is actually verifying the Android images. That feature is called Android Verified Boot. So we need to disable that. So in order to do so, we need to patch the LK image, so the little kernel image. And once it works, we can finally boot a modified Android image, so we can patch it to have a root access. All right, let's take a look at how we patch these things, and let's start with the little kernel bootloader. So first of all, little kernel is there is an open source implementation that you can find online, but here we are talking about something that was modified by Mediatek and Samsung. So it's not public, and there are many checks that were added compared to what you will find in the public version. So we had to reverse engineer this bootloader, and our strategy was the empirical approach. So we reverse it, we try to identify the checks, and we patch them, and we reflash the image on the device. We try to boot a modified Android image, and we get some errors most of the time. So you can see one example on the right. It's not very verbose. It's mostly JPEGs that are telling you that there is a problem. So you have to go back to step one, reverse again, try to find where this JPEG is involved and patch it again, and so on and so on. So ultimately, after some tries and after some time spending reversing this component, we were able to boot an Android image that was modified. So to highlight what I just said, this is something that piece of code that we extracted from Ghidra. And here, so there are no symbols. We gave the names to the functions. But what you can see is that we have a hash function that will actually produce a hash value, which will be compared to a stored hash value in a global variable. So there are many ways to patch this thing, but just by changing one assembly line, we could easily get to that point where we are actually hashing comparing the hash to itself, so that it's always true and we are always going to pass the check. All right, so thanks to these things, thanks to all the patches we applied on little kernel, we can modify Android. And let's take a look at how we can root it. First of all, you must know that there are two main images behind Android on this device. So the first one is the boot image that contains the kernel and the initial RAM disk. And you also have the super image, which contains most of the Android system. It's a dynamic partition, meaning it contains logical partitions inside. So here we have 4 partitions. And yeah, in the vendor partition, for example, you would find the trusted applications. So to root Android, there is this tool that is very known, at least in the Android community. It's called Magisk. So if you work with Android, you probably know that already. The tool is great. It works very well. It's very easy to use, and it will patch the boot image to disable some verifications and add some binaries that's in the end, you will be able it will help you to elevate privileges. So there is this binary SU that you can call. And when you do so, it will show a pop-up on the device so that the user can grant the privilege escalation. This is a problem for us because we are trying to play with a device we cannot unlock. So we cannot accept we cannot use the pop-up. So we had to apply several modifications on Magisk, for example, also because we wanted to use it from a laptop, and usually Magisk runs on a mobile device. So we applied little changes, and but yeah, in the end we were able to root Android that way. So once Android is rooted, we can access all the device encrypted files that Damiano mentioned, but it's still not enough to brute force the credentials because we need the key master won't decrypt the intermediate value that we presented because there is this auth token that Gatekeeper needs to share with the other trusted applications, which is why we need to take a look into the TrustZone environment. And in this device, it's called Tigris. As I said, it's the TrustZone environment designed by Samsung. You will find it on Mediatek system on chips, but also on Exynos system on chips. And behind that environment, you have 3 main images. The first one is called TEE1. You will find the code of the monitor, so the code running with the highest privileges on the device. You will find the kernel of the TE of the TrustZone OS, and you will find the userboot.so file that is also used to verify the next image, which is called TZAR. So it's an archive containing the root file system for the TE environment. And finally, you have the Android system image, super image, that will contain several trusted applications and drivers, so that Android will actually send the applications it needs to the trusted environment. So we won't give more details on Tigris. We won't have time to cover everything in this presentation. So yeah, we recommend this excellent blog post series online on the Riskio website. Yeah. So let's take a look now at how these Tigris images are involved in the boot process. Here again, we have a preloader that will verify the TE image before loading it in memory and loading all the components it contains. And then you have the teaser image that will be sent to the secure world, and it will be verified by the userboot.so binary I mentioned. Then whenever Android wants to run an application, it will send it to the secure world, and we have a component that is actually placed in the teaser image archive that is going to verify the trusted application before running it. It means that if we want to patch Gatekeeper, we need to disable all these steps. So we need to patch all the components that actually perform verifications. The first one, the preloader, is already disabled by the MTK client tool. So we just need to do the same for userboot.so and the root task. And yeah, so with that done, we can finally get to the Gatekeeper trusted application. So in the Tigris world, trusted applications are slightly modified ELF files. You will find a little header plus a footer and a signature on top of it, but if you remove that, you will end up with a classical ELF that you can load in any disassembler. And so these trusted applications are closed source, but the reverse engineering task is not too hard thanks to, first of all, the usage of libraries. So you will find some symbols, and in particular, there is this global platform API that comes as a library here. And you will find it's a standard API for TEEs. It defines many things such as memory allocations, crypto operations, and so on. So whenever you do the reverse engineering steps, you will encounter some symbols, and you will be able to find them on Google, and you will have a clear definition of what it does. So you don't necessarily need to go into the libraries to understand what's going on. There is also this reference implementation that is the TrustZone. It's the TE OS designed by Google, and it's particularly interesting to understand how things should happen. So yeah, we started our analysis by looking into the trusted applications of Trusty, and this is what we understood out of it. So the Gatekeeper application implements two main commands. We have the enroll and the verify command, and the verify command is the one that is used to verify the credentials. And it does the two following things. So first of all, it receives a password handle, which is derived from the user credentials, and it will HMAC it. So there is an internal key to perform this HMAC. And the value is compared to an expected value that is actually also coming from the normal world. It's actually present in one of the device encrypted file. And if the two value matches, Gatekeeper will create the new authentication token, and it will return a success to the normal world. Now, what if we can leak this HMAC key? We will be able to have the following strategy for brute forcing the credentials. We would first need to generate a new password. We would then use the key to HMAC the password handle. It will produce a value, and we will have just to compare the values with the expected values. And if it matches, we found the password, great. If it doesn't, we just go back to step one. The thing is that this is the trusty implementation, but it's not exactly how it works inside the Gatekeeper trusted application, even though it's very similar. Indeed, instead of having an HMAC, we have a custom function that is called KDF, so key derivation function. It can actually be an HMAC behind that. But it's not as simple as it would have been for the trusty implementation. It requires more work to get to that point. We need actually to reverse a driver that is involved in this KDF procedure. And from what we read online, it's also behind this crypto driver, there is a crypto processor that is probably handling the key. So we will also need to get to that crypto processor to leak the key. So we decided to go with a simpler strategy. Instead, what if we just patch the check so that it's always true? And that way, Gatekeeper will produce this host token, even with the wrong credentials. To highlight what I said, so this is a view of what you get when you reverse the Gatekeeper. You can see the TE underscore functions that are actually the ones of the global platform API I mentioned. So it's already some symbols that you can easily understand and look online. And you also have this function called TES, S maybe for Samsung. This one is not from the global platform API, and it's actually the KDF function I was talking about. All right, so we can now summarize our attack strategy as the following. So first of all, we patched Gatekeeper. We have access to the device encrypted files. Now we just need to leak the output of this first AES decrypt, as Damiano mentioned. And using this value, we would be able to brute force it because we can generate the application ID out of the credentials. And because the second AES decrypt is using Galois counter mode as an operating mode, it's also checking the authentication on top of the confidentiality, so it will fail if the key is wrong, meaning that every time we use a wrong password, we will get an error out of the decrypt function. So in order to leak the first AES decrypt output, we need to hook a process that is called system server, and it is the main process behind the Android runtime that is called system server, and this process is actually calling the initial function that will provoke the chain of calls up to the key master trusted applications, but the output will return in this process. And to do so, we are using another very known tool in the Android world, which is called Frida. This tool is an instrumentation framework that is quite handy to use, especially on Android. So we simply hook a function called decrypt from the synthetic password crypto object. And whenever the fixed function returns, we just get the return value that you can find here, which is the value we were looking for. All right, now we have all the components to start brute forcing. But before we get to that point, let's take a look again at this big schema and zoom only on the parts that is interesting for us. So the hashed secret you see on the right of the screen is derived from device encrypted file that we leak. We need to do that only once, so we don't really care about this step for the brute force. On the left, you have the first AES decrypt. We are able to leak the output of that. So we also don't care about this thing for the brute force proof of concept. So we end up with the following steps that we can translate into the pseudocode you see here. So we first generate a new password. We use scrypt to produce a token. And we concatenate the token to the pre-hashed value in order to make this application ID. We can hash this to produce the key, and finally we use the value we leaked using Frida along with the key in this AES decrypt function. And if it fails, we go back to step one. If it works, we found the credentials. So we implemented this little script that is working decently. Here we are executing it on a very powerful virtual machine. So it works for small passwords. It's probably something we want to improve in order to work for more digits than just 4. But you can see here that in 18 seconds we can find a very small pin code. So we actually have a video. All right. So we have the A22 Samsung device. Here I'm just starting it. Pay attention to the logo. It's the original one, so it's just to show you that it's the real device. We didn't really modify it. I will fast forward a bit. So the device boots. I am entering the pin code. Again, it's just to show you that the device is actually a normal one, but I will fast forward that part. Once I did this, I will simply short 2 pins to enter the boot ROM mode where we have the vulnerability. Note that this is only needed for one of the devices. The other one doesn't require to short any pins. You just reboot it with the cable plugged and it will boot into that mode. yeah, we have to use this device for the video because we obviously bricked the other one. So anyway, it's still not a problem for that kind of attack. So the device will boot. Here we are starting our proof of concept script, and we start by dumping all the images we need. It's going to be quite fast. We can also download directly the images from Samsung website. This step is not really needed. Now that we did that, we are simply patching, like we apply Magisk on the Android version. We patch little kernel, the TEE environment, and then we flash back the images. All right. Now I use the tool to start the device, bypassing the secure boot. Let me fast forward a bit. Okay, the device booted, and you can see here that we actually downloaded the files, the device encrypted files that we need for the brute force. Now we are running Frida in order to leak the first AES decrypt output, and we automatically insert a pin code from the script directly. And you can see the value here is the actual output of the AES decrypt. So we can now start the brute force script. I will fast forward a bit because the brute force is quite slow due to the fact I'm recording the video at the same time on my laptop. All right, so you should see the pin code that was found thanks to the brute force. It's 1106. Now, yeah, I will show you I'm showing you that the files are encrypted on the device. I'm entering the pin code, and I will show you that thanks to that they are decrypted. Here we go. Thanks. Okay. So that's it for the first part of the presentation. But this is for the old way of doing of protecting the data using the TrustZone. But since few years, they introduced in high-end devices security chips that also involved in the protection of the user credentials, and we will see how. If I can change the slide. All right, let's start with the architecture with this new model. So we still have on the right the usual system on chip that runs the normal world and the secure world. The only new thing is that we have an extra device, an extra chip, that is the security chip represented on the left, and it's completely separated on the hardware side. So we decided to play with the Titan M chip mainly because we already know it well. We had found a vulnerability in the past. Damiano will give more details about it later. And this chip is actually made by Google. It was introduced starting from the Pixel 3. And you will find it up to the Pixel 5a, because starting from the Pixel 6, you will find the new version of the Titan M called Titan M2. And so, yeah, this chip is based on ARM Cortex M3, and most of the code is divided into tasks. You have the main one that is the key master task, used to store the keys of the applications. And you also have one that's particularly interesting for us today, that is Weaver. And I will come to that later. So this chip will communicate with Android through the SPI bus. Now, the reason why Google introduced that chip, at least that's the reason they gave, is because due to the fact that in TrustZone, with the TrustZone, you have the secure world and the normal world that both share a lot of hardware resources, such as the cache, the RAM, and so on. It was proven that it's possible to perform some side channel attack. We have, for example, Rowhammer or cache-based attacks that were used by researchers to leak secrets from the secure world. So they decided to introduce this chip that also integrates some security features, like you will have a shield. You will have sensors, stuff like this inside. And the firmware is quite simple, as I said, so and quite small. Now, this is the schema of the the architecture, let's say, we have the Titan that talks with the chip using the SPI bus. And you have a kernel driver that will handle the SPI protocol, that it will expose an IOCTL interface. And you have a daemon called Citadel D in the userland that will handle all the communications with this driver. And finally, you have a set of hardware abstraction services. You will have one per functionality, so one for Weaver, one for Keymaster, and they implement the protocol to talk to the Titan M applications using protobuf. I also wanted to show you this memory layout of the chip. We can note a few things here, but the main point is that we have two regions called SFS, probably for safe file system or secure file system. And this is where you will have the persistent data. Another thing that is worth mentioning is that here, the addresses you see here are physical addresses, and the flash memory is directly executed by the microcontroller. All right, so let's now take a look at this Weaver application. It's actually rather simple. It can be compared to a dictionary in other in some languages. So it's a way to store key-value pairs. You actually have a limited amount of slots that can be used to store key and values. The keys will be stored in one SFS region, the values in the other one. And you have only 4 commands for this, including read and write. So if you look at the protobuf definition of the read command, whenever the system wants to read a value from Weaver, it will send a key, which is a 16-byte value, along with a slot number that comes from one of the device encrypted files. And if the key matches what there is in the slot, the chip will answer with the actual value, which is also a 16 bytes value buffer. Now, there is also a throttling implemented here, so we cannot just try to guess any keys like that. It's another protection you have here. All right, let's take a look again now at the big schema and how we can derive the CE keys. It will be a bit faster here because most of the schema here, you cannot see it very well, but most of it is the same as what we presented. The only part that changes is the upper part. So, here again, we have the credentials that are converted into a token. And this token is is hashed to produce a key, the Weaver key. It is sent to the chip whenever we want to read the value, along with the slot number coming from one of the device encrypted files. And when the chip, okay, I have to be quick. Anyway, the chip will return a value, and this value is going to be hashed. And to produce this hash secret, that will be concatenated to the token to produce the application ID. And starting from here, everything will be similar to what we found on the other schema. Now I will give the floor to Damiano to go on with the proof of concept.
Yes, so we will conclude the presentation with the second proof of concept we promised, this time focusing on the case of a schema that has a security chip involved. So this time we will start from a rooted device, so we won't go over the process of being root already on the phone. This is needed because we still need access to those files you have seen earlier. And then the additional part that is required in this case is being able to execute code on the Titan M to leak the Weaver values that Max has introduced before. So to do that, we use a vulnerability that we found last year. It's an exploit that allows only to write 1 byte to 1 with some constraints on the offset. It's a very limited primitive that we managed to turn into a code execution exploit. If you are interested, I recommend you to have a look at our blog post where we explain how we did it. But this is not the point of this slide. What we want to say is that we have a way to execute code on Titan M, and in practice we use it to create a sort of leak feature. So within the client that we developed to communicate with the chip, we added this sort of feature, exploiting the vulnerability that allows to read arbitrary memory in Titan M. Now, we use that to find these Weaver slots and values. How to find them is a mixture of a bit of reverse engineering and some hard-coded addresses in the firmware, and also a bit of trial and error. In the end, this is not so hard, as we will see later. So the brute forcing strategy boils down to the very top of the schema that you saw earlier, because we don't even need to worry about authentication and Gatekeeper and those AES decryptions anymore. All we need to do is to focus on that specific part of the Weaver, the key value derivation, we can say, where we actually use the credentials as token to retrieve the value. So translating this into steps, it's really just generating a password, encrypting it, creating a hash of this token, and then comparing it with the leaked Weaver key. So yeah, again, the same very simple script that is written in Python, so it could be made much faster than this, which, however, manages to find the password relatively quickly. And also in this case, we have a little demo that I'm going to show you. So the first thing we need to do is grabbing here you have the usual data that are encrypted. When we first boot the device, we're gonna grab some. First we're gonna run our client to communicate with the chip. We are killing the normal daemon, otherwise we can't communicate with the chip itself. That's where we need root, by the way. And this is the key that is being leaked. I'm gonna just stop for a moment to show you that at the end of the day, it's not that hard to find it in memory. Like you can see in a 0x100 bytes is the only part that looks random. That's a SHA, right? The rest is null bytes or our attempts, where you see the A's and the C's. So okay, once we have that little buffer, we will just take the DE files we need from the data system DE path. Those are the files that we need to start from to get the to form the token that is going to be needed when sending it to Titan M. So yeah, we will just extract these files and then just launch our brute forcing script with the key we leaked and the files that we extracted from the device. Now this is going to take a little bit of time, also because I'm running it on my laptop. But at some point, it is gonna give us the same password as before. Yes. Which we then insert into the device to unlock it. And then from here on, we won. All right. So to conclude, I guess the very first thing that is worth noting is that file-based encryption is a rather well-designed system. As you have seen, it's interesting to see how ingredients from a bit everywhere are combined together. And when there is some crypto involved, of course, there's no way out. You need those very bytes to get back the key you're looking for. So you have files that are owned by privileged users, so that you have to be root on the phone. You have some keys that come from the trusted execution environment. And when it is available, you also have something that comes from a security chip. So this is very interesting because, again, in such a complex schema, you add one component that in practice doesn't alter at all the whole performance and the overall schema, but you need an extra ingredient which requires an extra exploit and a very big effort from the attacker's point of view. So yes, you need multiple bugs to break the system, especially when there's a security chip involved. Exploiting the main SoC is not enough, even if you have a very powerful bug like the MTK one that we showed. But at the end of the day, you still need to brute force the credentials, as I said. So if your password is very long, well, maybe it will take 10 seconds to unlock your device, but at least it will make the attacker's life much harder. And with that, thanks a lot, and we are happy to take any question.
Thank you, guys. Thank you. And yes, indeed, we have some time for questions. And the first question comes from here.
Hi, thanks for the great talk. I do have one question about the first set of phones you exploited. Did you actually flash the firmware, or were you just booting it? And if you did actually flash it, did you trip the Knox bit, if present, in that device?
Which bit? Yeah, we flashed
the Knox security bit that is used in enterprise phones.
We didn't look into that, so no, we didn't.
Okay, thank you.
Do we have any other questions in the audience?
Sorry, yeah, on these devices, I'm not sure there is Knox. You mean Knox, the Samsung feature? Yeah, I'm not sure there is Knox at all on this.
Perfect. Any other questions from the audience? Raise your hand. All right.
You said you bricked one device. What did you do wrong? Can you talk about that?
We flashed too many partitions, and the device, I mean, the point for the proof of concept for a demo is to show you a device that is not showing warnings. And our device was always showing warnings.
Okay, so it's still working in a way.
Thank you. Any other questions? All right. I think we can ramp up this talk. Let's give a warm set of applause to the guys for their effort.